to take a look at inferences for difference between two population means. We are in section 5.3. So the assumption in this section is that we have two independent samples. Now, coming out of section 5.2, I believe it was, where we addressed the situation where we had a paired t-test, assuming we had dependent samples. So again, in section 5.3, in this section, we're going to change that assumption that we have two independent samples. So we're going to have two situations here. We're going to take a look at two conditions. The first condition is the population standard deviations are unknown and they are different. And the second situation we're going to take a look at is same as number one. The population deviations are unknown, but the difference is that we can now assume equality of the deviations in the population. So our first form of inference is our point estimate. How do we estimate the difference between two means, mu1 minus mu2? Well, let's take a look at the sample means, and we're just going to compare this two sample means. So our statistics is going to be x bar 1 minus x bar 2. Now, for the first situation where the deviations are unknown and different, the theoretical work behind this ends up being, assuming we are sampling from two normally distributed populations for x1 and x2, then the sampling distribution of our statistic, which is x bar 1 minus x bar 2, ends up being normal. The center of the distribution is going to be exactly the same as mu1 minus mu2. But its a standard deviation is going to be given by this formula. Now again, sigma 1, sigma 2, these are the theoretical deviations for the sampling distribution of x bar 1 minus x bar 2. However, because these are unknown, we're going to replace them with their sample equivalents. Okay, and that's what I have here in my first bullet. Since we don't know the population deviation, so we have to estimate them using S1 and S2. That's what we use in here. So our other form of inferences are going to be in the form of a confidence interval and then hypothesis test. Now I have the formulas here for those who are interested, but we don't want to do this by hand, and we're going to use Minitab actually to do this. But I have the formulas for you. So the confidence interval formula is going to be our point estimate, x bar 1 minus x bar 2, plus or minus the margin of error. That's what the right side is. So here we're going to use a t multiplier, and this is the square root is exactly what's up here. You see the square root? We replace sigma 1, sigma 2 with s1 and s2. The degrees of freedom for this one, I'll talk more about the degrees of freedom later on as we look at an example. But for now, if I do this by hand, I'm going to choose the smaller of n1 minus 1 or n2 minus 1 for our degrees of freedom. However, the softwares do not do that. The softwares actually use what we call Satterthwaite approximation, which I'll show you later on. And that's what Minitab uses. When we test the hypothesis, the null hypothesis is that the two means are equal. There's no difference between them. And our test statistic is going to be this formula that you see down here. That will be our test statistic. And our decision rule, of course, we're just going to follow our p-value criterion for our decisions. So we're going to reject the null if p-value is less than or equal to alpha, the same as before. Now, in the second condition, second situation, that's when the assumption was that the two deviations are unknown but equal. Now, the case where they are equal, do we assume that they are equal? In this case, what we need to do is we need to average them. Averaging of the two deviations from the sample is called pooling them. So what we do, in fact, is we pool the sample deviations, and this is the formula for that average standard deviation, if you will. Again, the reason we average them because of the assumption that they're equal in the population. but the samples are not going to be equal. So which one do I use? Well, let's average them. And this average actually is a weighted average. It's weighted by the sample sizes. So our formula for confidence interval is going to be adjusted slightly. What was under the radical, let me go back up. See, under the square root here, we have S1 squared, S2 squared. Well, if these two become equal, by pooling them, then I can factor them out. I do a little bit of algebra. Not difficult, but anyway, that's how it ends up to be. The degrees of freedom for this one is going to be N1 plus N2 minus 2. Okay, it's not going to be that Satterthwaite approximation. Our test statistic for the same hypothesis is given by this. Okay, and again, we do this in Minitab, so we don't need to know these formulas. So here we go. It's just kind of a summary of what we did just now for the pooled case. Now, the pooled case is actually the more common way of doing this because it works directly with analysis of variances. Okay, so here we go. We want to perform a hypothesis test to compare two population means mu1, mu2. And here are the set of assumptions we have. We have simple random samples. That's always the ongoing assumption in all of our work. We have independent samples in this section. And the population where we sample from, those two populations, one is for x1, one is for x2. Those are assumed to be normal, or each of those have to be at least 30. Large samples in the eyes of central limit theorem means at least 30. So each sample size must be at least 30. And then, of course, in the case of pooled, the equal population deviation. Okay. And these are the form of the alternative. The null says the two are equal. And this is our test statistics that I had up here. Let's see, right in here. That's exactly what's down here. And the difference is, see that SP out, when you take square root of S sub P squared, pooled variance, you take the square root, you can bring it outside, and it becomes SP. So anyway, that's what that is. And using p-value approach again, if p-value is less than or equal alpha, we reject the null hypothesis. Okay. And for our confidence interval, we have similar kind of formulas here. Okay. So this is the formula that I had earlier. Same set of assumptions. All your assumptions for hypothesis tests and confidence intervals for the same parameters that we test these for are the same. Okay, now let's take a look at an interesting exercise here. In this exercise, it's called doing time. Okay, so for this exercise, it reads: the Federal Bureau of Prisons publishes data in prison statistics on the time served by prisoners released from federal institutions for the first time. Independent random samples of released prisoners in the fraud and firearm offense categories yielded the following information on time served in months. So here's the data for the two groups, fraud and firearms. So if I just kind of take a look at these, and by the way, the sample sizes here are equal. They don't need to be equal. It just so happened they made them equal here. They don't have to be. Could be, but not necessarily. So look at the times they spent. These are the people that were sent to prison and did time on for fraud. As little as almost 4 months and as high as about 1.5 years maybe. But for most parts, most of these numbers are less than 12 months, right? So less than a year. And by contrast, take a look at the time served for firearms. Most of these are in double digits. So as high as almost 2 years, right? 25.5 months, 2 years. And the lowest was this double digit, 10 months. Okay, so just by looking at these, it looks like you would expect to do more firearms, right? More time for firearms than you would do for fraud categories. Okay, and here at 5% significance level, that's our alpha. Do the data provide sufficient evidence to conclude the mean time served for fraud is less than that for firearms offenses? Now they give you some statistics here. Don't worry about these numbers, because again, what we're going to do is we're going to input this information into Minitab and run our procedure in Minitab. Okay. And then later we're going to do a 95% confidence interval for the same thing. Okay. Now, I actually ran this in Minitab. Let me show you the output, then we go to Minitab in a minute or a few minutes. So here you go. This is part 1. Assuming population deviations are unknown and different. Okay, so here what we're doing is we're doing a 2-sample t-test and the confidence interval for fraud and firearms. So the method here, mu1 is the mean for fraud category, mu2 the mean for firearms. The parameters difference between them is what we're interested in. And notice I've highlighted underneath that phrase, we're assuming equal variances are not assumed. Oh, sorry, assuming equal variance is not assumed. But anyway, for number 1, remember, we just have unknown but different. So we are not assuming equal variances. And this is what I was talking about. Satterthwaite's approximation is right in here. The timeline for this is around 1946, I believe. So the procedure is almost about 60 years old. Okay, we're just shy of that, about 55 years old. Okay, and there you go. Pretty arcane formula, but again, you don't have to do this by hand. But this is what Minitab is using and softwares use. And you can see right in here, see the degrees of freedom is 17. The sample sizes were 10 each. So if we follow this formula, and here what are these cryptic notations, by the way? S1 squared, that's the first sample variance, N1 first sample size, S2 squared is second sample variance, and 2 is the second sample size. And that's what those are. Then you do this convoluted arithmetic right in here, and you should get 17. Okay, and you always round up for degrees of freedom. Okay, so there you go. That's why it's 17. But anyhow, now take a look at these statistics that came out of this Minitab. For one thing, the difference. See, this is x bar 1 minus x bar 2, which is a point estimate, a single guess at mu1 minus mu2, the difference between the two population means. So a negative 8.66 means you would expect to do about 9 months less for fraud than you would do for firearms. Okay, and here's a 95% confidence interval for the difference. It runs anywhere from -4 to -13, means anywhere from 4 to 13 months you would expect to do less time, anywhere from 4 to 13 months for fraud as opposed to firearms. Our hypothesis here, because the statement was, would you expect to do less time for fraud than firearm offenses? So our alternative is left-tailed, and our p-value is 0 to 3 decimals. I believe if you go to 4 decimal, it's going to be 0.0004 is what I recall this being. Okay, so definitely very small p-value, which means the null must go. If p is small, null must go. So null hypothesis will be rejected. Clear and convincing evidence against the null. So we're going to reject this null hypothesis. And when we reject the null, we're going to side with the alternative, and the alternative says you expect to do less time for fraud. And then right down here what I've done is I actually look at the box plot of fraud versus firearms. Remember, the assumption was the two population are normal, and the box plots kind of support that. You see that? You have this box plot of a normal distribution, almost looks like that. I would like to for this upper whisker coming out of the box would have been a little longer. That would have been perfect, but that's okay. This one, actually, it's almost normal also. You could these could also pass for uniform distribution. But again, sample size is so small that the box plots even may be misleading. Okay. Now, we actually, and maybe I'll show you how to do this. For small samples, we usually run a QQ plot, and I'll show you that in Minitab. The QQ plots are a better way of assessing normality than box plots or histograms are, because for small samples, again, histograms are meaningless. Okay, now running this using the second option, assuming equal deviations, where we pull the two deviations from the sample. So this part is the same. Difference me1 minus me2. Notice here we are assuming equal variances now. So that's consistent with what we're doing here. And look at our degrees of freedom now. It's 18, huh? Remember it was 17 for Satterthwaite's approximation. So it's now 18. But that's not going to materially change it. And I'll show you how that degrees of freedom of 18 was created. That's simply n1 plus n2 minus 2. Much easier than Satterthwaite's formula. And there we have it. But notice, by the way, look at the p-value. It's the same. Our test statistic 4.06, of course, is not going to change, right? Because that's based on the formula. It's the only difference between the first procedure, first one, versus second one, is just the change in degrees of freedom here. Okay. And look at confidence interval from -4 to -13. That's going to change. It's going to go, look at that, exactly the same. So that's not going to change either. Again, the only difference is in the degrees of freedom. And of course, the pooled deviation here is 4.77. That's what's used. As opposed to up here, notice there is no pooling of deviations in here. Okay. And our test statistic again is -4.06. -4.06. So the differences were not even notable here. But again, for most parts, personally, I always run a pooled t-test for problems of this type. Okay, so our decision is to reject the null hypothesis, and our conclusion is that on average, the time served for fraud is less than that for firearm offenses. Okay, and now let's go to Minitab and take a look at this. Okay, so now we are in Minitab. So let's take a look and see how we're going to do this. Now, I actually typed in the data here. But remember, you can type this up in Excel. So if you already have your data from Excel, you can actually import it into Minitab or just kind of copy paste it into it. Okay, so this is what the data is. Let me shrink this area a little bit so you see the raw data here. Now there you go, minimize as much as I can so we have more of the viewing window for the output. Okay, so let's actually go and run our procedure. So in order, I was going to show you this. Let me go on the graph and see if I can find that QQ plot. And there you go. That's what this is. It's the probability plot. Test whether your data follows a particular distribution. So remember, I use box plots, but this is actually better for small samples. You can look at multiple or single. Let me show you single first. Okay. So graph variables, fraud, firearms. Now the distribution here, you can actually tell it to test whether it follows a normal distribution or all of these other distributions. So I'm going to stay with normal. Now historical parameters, let's see. These, let me see if I can get away with just saying okay. Yeah, that's fine. But so see, by doing that, what the software does, it actually calculates the mean and deviation or the normal distribution from the data that it's working with. Let me just hit OK and see what happens here. And there you go. So this is a probability plot for fraud. Let me bring it up. And there you go. Now don't worry about these confidence bands that are around it. Okay. Now, the idea with a probability plot, again, these are called PP, probability plot, PP plots, or some call them quantile plots or QQ plots. But again, forgetting about these confidence bands that you see around the data. If this data follows a normal distribution, you would expect all these blue dots to fall along this line, this 45-degree angle line right in here. So this is actually pretty good. You can see how the data is almost along that straight line. Okay. Now, if you actually hold on this, you actually get the data points here. Okay. But anyway, so it looks like the distribution of time served for fraud is indeed following a normal distribution. What this other thing that pops in is when I go over the line, you see that? It just shows you the numbers that were used to construct this line. Okay. And these are actually percentiles that you see. 99, 98, and so on. 97, these are all percentiles. So don't worry about the details. It's just remember, all we want to know is whether these blue dots fall on that straight line. If they do, the data follows a normal distribution. So hit OK on this one. Remember, there's two of them. We just did this for fraud. So it looks like time served for fraud follows a normal distribution. And check out this one. What do you think? This is the amount of time served for firearms. See right down here, firearms. Again, it follows pretty close to that straight line. So the assumption of normality in this case is reasonable. Okay, I didn't do that in my notes. I just thought about doing this. I use box plots. But again, these are better, much better than box plots or histograms or dot plots. Dot plots are almost meaningless when it comes to small samples if you use them for the purpose of shape. Okay, so let's actually now go and run our t-tests. So to do that, you go to Stat, Basic Statistics. You're going to cut across, go down to 2-sample t, and there you go. So we're going to look at 2-sample t-tests. Click on that. Now, because I did this before, I actually inserted those into my notes, so that's why that was already populated. But when you actually go in here, these should be empty, and once you click into them, you should see these 2 columns that are already in place. C1, C2, fraud firearms. Those must be activated. So if you double click on fraud, it brings it into here. In the next field, double click on firearms. It imports it into that field. Now your options here, by the way, if you have summarized data, that means you don't see the data, but they give you like X bar 1, X bar 2, S1, S2, N1, N2, then you would use this. Let me show you. You see that? So if you have summary data, but for most parts we don't, we have raw data. And there you go. And it could be both samples are in one column. That would be if, let's say, both of them were indeed in one column, but in our case they're in its own columns, 2 columns. Here, if you click on graphs, you have option of individual value plots or box plots. That's how I got my box plot. And I cancel that because I use QQ plots. In the options, and there you go. So the difference is sample 1 mean minus sample 2 mean. That's our statistic. The confidence level, keep it at 95. It doesn't matter because we want to do a hypothesis test first. Remember, we're doing a left tail test. That is less than. And then uncheck. Yours default, that's uncheck. Mine was checked because I ran it the second time in my notebook, assuming equal variances. So for you, when you do it, it should be unchecked, and keep it unchecked. With unchecked, we're doing our first criterion without assuming equal variances. And then hit OK. And OK again. And there you go. This is how I got that output. Now, this is again the method that's used is the difference between two means. Equal variances are not assumed for this analysis. So that's our first criteria. Here are the descriptive statistics. Look at the averages for fraud: 10 months, average firearms almost 19 months, give or take 5 months. Now, one thing that by default you get is this information right in here, which actually we don't need it. Okay, this confidence interval, that's not how I got my confidence interval. Okay, this is like a one-sided confidence interval. Ignore this. The difference between the two means, that's 1878 minus 10.12, that's going to be 8.66. The reason it's negative, because you're doing mu1 minus mu2. So what Minitab is doing is actually doing x bar 1 minus x bar 2. So that's 10.12 minus 18.78, and that's how you end up with a negative difference. Remember, a negative difference, look at that. A negative difference means lesser time for fraud than firearms. Our test, hypothesis test, again, the null is 0, alternative is less than 0. Our p-value is almost 0. Again, to 4 decimal, that's going to be 0.0004. Okay. And how do I know it's 4? Because I ran this earlier to get more exact number, and that's what I got. Okay, and there you have it. So this was again the first assumption that deviations are not equal. Okay, we are not assuming they're equal. And let's say we want to do our 95% confidence interval now, not the one-sided, but the actually two-sided confidence interval. So for that, you actually have to go and rerun the procedure. We go to to sample, go to options, and just to get the correct 95% confidence interval, make sure this is changed to a two-tail alternative. There you go. So this way we're not going to get the one-sided confidence intervals. And there you go. See, estimation for difference in the confidence interval. The only thing that's different is this now. Okay. And of course, let's see, our p-value, don't worry about this. Is now this time ignore this one. Remember, the only reason I chose two-sided alternative is to get a confidence interval with a lower and upper limit. So you may say, well, p-value was 0, why is it 0.01 now? Because look at the alternative now. It was less than, now it's not equal to. So ignore this part of it. Ignore the test now and just use the confidence interval. Okay, and let's rerun this assuming equal variances or deviations. You go basic stat, to sample, just like what we did a moment ago. Same variables. In the options, there you have it. You see that? Assume equal variances. Change that to less than to run our hypothesis. And there you go. And right up here it says equal variances are assumed for this analysis. So if the problem requires or mentions assume equality of variances, you pull them. And there you have it. And again, now to do a 95%, notice we don't want this one-sided confidence intervals. In order to get a two-sided confidence interval, that is a lower and an upper limit, not just in this case an upper limit. We need to change our alternative hypothesis to not equal to. So I'm going to go to stats and options, change this to not equal, so I can get 95% confidence interval now correctly. And there it is. Okay, so that's what we want to do in this lecture. And hopefully you followed everything we did. Again, it's pretty straightforward. And with that, we are actually done with this section. Again, we just talked about or learned about inferences for two population means, assuming equal deviations and one that does not make that assumption. Okay, and that will conclude this video.